and private organisations, largely in the field of what you might loosely call number crunching. So I've worked for people like HMRC, Barclays Bank, the British Library, the British Film Institute, and so on. I am not an engineer. You all know more about engineering than I am. I'm going to try not to embarrass myself too much. What I do is mathematical modelling, statistical analysis, and software related to number crunching. So I take large numbers of numbers and try to make some sense out of them. So what am I doing here? Well, about 10 years ago, I joined a local group who were reacting to a proposal to install a wind farm around our North Yorkshire villages. Some of us started to look at the proposal and its implications and started to question the facts about wind power. A couple of years ago, we started to analyse the claims about wind power with a national perspective and to look at how wind power fits into the UK's energy future. And what we discovered is that some things don't add up. Some of it just doesn't make sense. Now, at this point, can I just check with Sue? You can hear me okay? And
yep.
Everything okay? Good.
Yes.
I assume anybody will notify Sue if they can't. So, first of all, I'm going to just talk very briefly about what the national grid is. I appreciate you probably all know what it is anyway, but just for the benefit of clarification, the national grid is the system operator of Great Britain's electricity and gas supply. Now, it's important to recognise that it's Great Britain, so it doesn't include Northern Ireland. It's England, Scotland and Wales. Northern Ireland is covered by the Irish grid. And it's the company that manages the network and distribution of electricity and gas that powers all of our homes and businesses. The national grid network is made up of high voltage power lines, gas pipelines, interconnectors, international interconnectors, and storage facilities that together enable the distribution of electricity and gas. So that's what the national grid is and does. Within the national grid, there is a section called the Electricity System Operator, the ESO, who I'll be mainly referring to. And what they do is basically check that we're getting enough electricity. They don't actually generate it themselves, but they plan for how much we need. They work out how to distribute it. They make sure it's distributed. They're basically responsible for keeping the lights on. In this presentation, I'm going to focus on electricity, although I will occasionally mention gas. Now, there are many organisations involved in electricity supply. And if you want to find a page, if you're not familiar with the national grid and you want to know who does what, if you just Google what we do, national grid ESO, it will tell you who does what in the national grid. And the national grid, as I say, is the main organisation I shall be referring to. So what does electricity supply and demand look like now, today? I'll show some typical examples, but with some specific ones as well. And it's the extreme cases that are important, as they're the ones that cause the biggest problems. The pattern of electricity supply and the pattern of electricity demand is surprisingly consistent over the year, although the demand is of course greater in winter months. And very importantly, in this presentation, I'm going to ignore the effects of the pandemic. What's happened in the pandemic is that demand has been not only reduced very considerably, but it's been spread differently throughout the day with people doing homeworking and so on. So the examples I'm using are mostly from before the pandemic, although the numbers between now and then haven't really changed that much. You will have all read in the news, I'm sure, in the middle of last year, how celebration was of 68 days without burning coal, for example. Well, that was largely due to the fact that demand was low enough that we didn't need coal. Under normal circumstances, I don't actually believe that would have happened at all. So here's the typical week in January. This week is from January last year, the week beginning the 6th of January. The red line is the demand line. We have what I'll call a base load of about 25 gigawatts. And then over the 7 days of the week, it peaks in the evening, apparently when Coronation Street or EastEnders start or end, I'm not sure which. It builds up to that when everybody's eating their dinner and so on, and then it goes low overnight and so on. The cycle continues, and obviously we use more during the week than at the weekend. How is this demand satisfied? Well, first of all, nuclear is one of our steady supplies. It supplies part of the base load, usually about 6 or 7 gigawatts. Then we have biomass. Now, I'm trying to be consistent in the colours here, but it doesn't really matter because the main ones to look at are the red one and the black one. The black one is the total supply of the ones that I've talked about. So as you can see, biomass, which is also reasonably steady, takes us up almost halfway to the base load demand. Now, at this point, what we include next doesn't imply that this is the order in which these things happen. I'm just explaining really how the gaps are filled. And the first important thing that fills it is wind. Now, wind, of course, we have no control over. That's how the wind was in that particular week. And when we add that to the existing nuclear and biomass, you've got pretty much the same pattern. It just moves up a lot. Very importantly, note that with wind, we still never achieve demand. The main supply that enables us to achieve demand is gas. And when we introduce CCGT, closed circuit gas turbine gas, that's what happens. And as you can see, I always imagine somebody at the ESO with a little dial or maybe one of those sliding things like a recording console saying, oh, we'll have a bit more gas or we'll have a bit less gas, and just following the profile of demand. And that's pretty much how it works when you look at it in this way, I should say. Now, on top of that, we have interconnectors. Now, they're currently shown by the blue line at the bottom, and these are the international interconnectors. At this time, there were 5 of them. We now have 8 listed, although 6 of them really are in use. But at this time, we had 5, 1 to the Republic of Ireland, 1 to Northern Ireland, 1 to Belgium, 1 to Netherlands, and 1 to France. And we can import and indeed export power to and from those 5 locations using the interconnectors. And in an ideal world, when we're short, we can get it from them. And when we've got too much, we can send it to them. If only life were that simple. So as you can see, supply is now getting pretty close to demand. Let's add something else. Let's add good old coal. And there we have just about satisfied demand in that particular week. Now, there's a gap still, as you can see, and the gaps are actually filled by a number of other very minor sources: hydro, storage, oil, OCGT, various other minor sources. And they all sort of trudge away. Some of them are a little bit controllable, some of them aren't, but they fill up the gaps. And that's basically what happened in that week. So why do we need to change? That all looks pretty good, but why do we need to change? Well, the reason we need to change is that we need to reduce greenhouse gas emissions. We need to be net zero by 2050. And in fact, according to the 10-point plan announced by our Prime Minister in November, we require to get down to 64% of 1990 levels by 2030. So we've actually got a short-term target as well as that longer-term net zero target. So how are we going to eliminate these greenhouse gas emissions? How are we going to get down to there? Well, there's a lot of things we're going to do. We're going to reduce the energy needed for home heating. And in fact, there will be general improvements in energy efficiency. We're going to switch from fossil fuels for transport. The most noticeable one of those is the ban on the sale of petrol and diesel cars by 2030, the ban on the sale of hybrid cars by 2035. We're going to stop using coal to generate electricity. We're going to reduce gas burning, including for electricity generation, and pretty much to zero by 2050, although it's a little bit more staged than coal is. And there are various other things we're going to do to eliminate greenhouse gas emissions. So how do we set about doing this? Well, we have quite a few approaches. One of them is to use more renewable energy sources. And the most notable energy source that's going to be introduced is hydrogen, and we're going to start generating hydrogen in a green way. And in fact, hydrogen will be providing up to about 60% of our end user needs by 2050. It provides a very small amount at the moment, but it'll be about 60% by 2050. And we're also going to use technologies that can reverse emissions. So we're going to use carbon capture and storage, CCS. We're going to implement more energy storage to overcome intermittency issues. So given that we won't have good old controllable gas anymore, and we're still going to get those peaks and troughs in the wind, we're going to cover that by having storage, more storage, including V2G, vehicle to grid storage, that I'll talk about more later. And we're also going to use more sophisticated technology to optimize energy use. So demand side response, and basically we're going to be encouraged to use electricity at times we don't usually use it. We're trying to try and flatten the pattern of demand, basically, reduce the peaks, bring the troughs up a bit, make it a bit easier for our new supplies to cope. There are many such different approaches, and I'm going to talk about some of those in this presentation. So what's the plan? How are we going to achieve all of this? Well, the plan is embedded in a set of future energy scenarios documents. It's a set of publicly available documents. They cover gas and electricity. There's a new version each year, usually in the summer, usually comes out in July. There is a plan. I'll use the word plan with a small p because they don't like you to actually call it a plan, but there's a 5-year forecast for the next 5 years, which is pretty much what's supposed to happen. And then there are alternative scenarios right through to 2050. And the scenarios reflect different combinations of rate of change, decarbonisation, and so on. And I'll explain the scenarios in a moment. So the scenarios, what are they? Well, the first one is the steady progression scenario. And this is the one which doesn't get us to net zero by 2050. The other three are system transformation, consumer transformation, and leading the way. In this presentation, I can't cover all of those because you'd be here for hours. So I'm going to concentrate on the most ambitious one, leading the way. These are based on different levels of societal change and speed of decarbonisation. And if you want full details of all of these scenarios, just Google the future energy scenario documents. They're big documents, there are a lot of them, and they will tell you in great detail about all of those scenarios. But just for a pictorial representation of the four, little grey steady progression in the corner there, it gets us part of the way to net zero, but it doesn't involve us changing what we do much. It doesn't involve decarbonising very quickly. It just sort of nudges us in the right direction. Leading the way, on the other hand, gets us as far as we think we can possibly get by 2050, including actually below zero carbon, below net zero, as I'll explain in a moment. The other two achieve the same level of decarbonisation pretty much, but consumer transformation involves more personal actions by each of us. So we have to do more, like getting rid of our petrol cars, changing the heating in our homes and so on. System transformation involves more, if you like, centralized change, more to the way the whole thing works rather than to what individuals do. So what's all this going to do to greenhouse gas emissions? Well, the position we're at the moment, the 2019 value at the top left there is almost at 500 it's almost at 500 million tons of CO2 equivalent. And if you look to the right to 2050, with system transformation and consumer transformation, it gets to zero. With leading the way, it actually goes below zero. And with steady progression, it gets about half of the way there. So 3 of them succeed and 1 of them doesn't. What does steady progression mean? This is the one that doesn't get there. Well, we don't achieve net zero. It's least progress with decarbonisation, but it's using credible steps. Heat and industrial processes become more efficient and slowly decarbonise. There's less use of new technologies, so we don't use this carbon capture and storage technology, BECCS, that I'll explain in a moment. We don't go so much in the direction of using hydrogen for everything. This means that we don't need to make difficult decisions, unpopular decisions, we don't need to deal with uncertainty or expense. I can think of at least one government that would probably appeal to. But in general terms, this is the easy option. This is the one that gets you part of the way, but doesn't involve too much stress. Leading the way, on the other hand, says we fit heat pumps, we have our own energy storage, heating systems respond to market signals as well as user control, so there's great incentives to do the washing overnight and heat the house overnight and be cold all day, etc. Smart appliances in the home help us to manage energy demand. More people use public transport. Private cars are electric and use or provide V2G storage. And businesses switch, process and or relocate to make use of hydrogen and to make use of BECCS facilities. And consumer choice influences the products on offer. So we're all very much driven to do everything we can to reduce greenhouse gas emissions in the ways I've already described and many others as well. System transformation, it does meet the net zero target, but it has the least consumer impact. There is high use of hydrogen for heating and other energy demands. So over 65% of homes use hydrogen for heating by 2050. And in fact, hydrogen supplies 59% of total end user energy by 2050. More details in the FES documents. Consumer transformation, that's the one that involves us more. It meets the net zero target. We follow here a pathway with relatively high consumer impact. So we have a high level of electrification for heating and other energy demands. Lots of us have gone down the electric cars route. We have to by then anyway. We're using electric heat pumps. We're using a lot of DSR technology and so on. And again, full details in the FES documents. So in terms of overall customer energy demand, if you look at the top row there, in 2019, the energy demand for industry and commerce, 494 terawatt hours. That includes electricity, gas, oil, petroleum, hydrogen, biofuels, everything, although it does exclude aviation, rail and maritime. I'll talk about one or two of those a bit later on as well. Residential use, 486 terawatt hours. Transport, 440 terawatt hours. So our total customer energy demand in 2019, 1,420 terawatt hours. If you look at the equivalent totals using the four scenarios, you can see how much that's reduced. Not very much in steady progression, but in the case of leading the way, customer energy demand is less than half of the level it was in 2019 by 2050. And in areas like transport, we're only just over a quarter as much energy demand. Residential, industry and commerce, about half the amount. And then with the other two scenarios, you can see the effects in those as well. So we're talking about very great reductions in demand. So what's the plan? The key features of the plan? Well, the key features depend on the scenario. One of the features of the plan is that electricity demand will increase following several years of fairly steady decrease. You may be a little bit surprised in terms of the chart that I just showed you, because you may think, well, surely demand's going up. More is going to be done with electricity, but we're going to be cleverer with the electricity that we are using. We eliminate coal and gas. Private cars switch to battery electric vehicles. There is an increased generation of and use of hydrogen, including production of green hydrogen using electrolysis. And the intermittency of wind and solar are handled by interconnectors and storage rather than coal and gas. So we deal with that pattern of demand by getting energy from the interconnectors and by having plenty of stored energy available when we need it. So at the heart of this are two new technologies, BECCS and hydrogen. And to me, these are two of the greatest areas of uncertainty and risk. And I'll talk about each of those a little bit from now on. The national grid makes it clear that these must be deployed for net zero to be achieved. It can't be achieved without both of those being deployed to quite a considerable level. And we need industrial scale demonstration projects of both this decade. We do not have industrial scale implementation of either yet. But by the end of the 2020s, we need good large-scale demonstration projects. And in fact, depending on the scenario, we actually need to be using them to some extent by then as well. Let's talk first about BECCS. It's bioenergy with carbon capture and storage. This is a process for extracting bioenergy from biomass and capturing and storing the carbon, thereby removing it from the atmosphere. So we grow some biomass, and then when we process it, the greenhouse gas carbon dioxide is extracted from the atmosphere by the biomass when it grows, and when it's combusted, we store the carbon away. So the carbon in the biomass comes from the greenhouse gas carbon dioxide, which is extracted from the atmosphere by the biomass when it grows. What about hydrogen? One of the good things about hydrogen is that it provides a transportable way to store energy. If you can make hydrogen, you can transport it around, which is really quite a useful thing to be able to do. And the other great thing about hydrogen is that it produces no carbon at the point of combustion. It can be produced from either electricity by electrolysis or natural gas, typically by methane reforming. At the moment, we do have some hydrogen production, but I think less than 1% of it is by electrolysis. The vast majority is actually done by natural gas processes, methane reforming and so on. In the leading the way scenario, it will be produced wholly by electrolysis. And typically we'll have offshore wind farms, and the excess electricity, of which there will be much from offshore wind, because a lot of the time we'll have far more than we can do anything with, will be used to power electrolysis. This will happen in deep water sites. The hydrogen will be stored locally and or be produced and stored and then pumped to shore and used ashore, transported around as necessary. Now, I'll come back to solar in a moment because there's a little solar factor in here as well. But just think in terms of leading the way that we are using electrolysis, excess offshore wind power to electrolyze hydrogen, to produce large quantities of hydrogen. This generation would require an additional 148 terawatt hours of electricity per annum. But if you project wind patterns forward and look at the growth in offshore wind facilities, excess wind should be able to provide that amount of electricity, which we couldn't otherwise use. So in a way, it's a really great idea because we're using stuff that would otherwise be wasted, or we could sell it to the French or so, or the Irish or somebody. But otherwise, we can't do anything much useful with it. Why not make some hydrogen? It's on the face of it, it's a good idea. So other things about hydrogen, which are very important. It can offer a number of best options, or at least alternative options for all sorts of things. Transport requiring greater range, volume or weight. Battery is not a good solution for large commercial vehicles and ships and things like that. There is going to be an increasing move to powering those with hydrogen, and hydrogen is much more suited to that purpose. In fact, the leading the way scenario in the FES documents assumes that a large proportion of heavy vehicles will go down the hydrogen route. It can provide heat for various industrial processes. It's a good alternative, efficient form for home heating. It's more like current gas heating than the heat pump option. It can provide additional energy storage, which is very important, and it can also perform an electricity system balancing function as well. So one other thing just to briefly mention here, I'm going to skim over this quite quickly. I've not really mentioned solar. Why don't I mention solar much? Well, it has a very limited supply to the grid at present. Almost all solar is used locally. You walk around our villages, half the people have got solar power and they reckon it's great for their roofs, but they're mostly using it to supply themselves. You can sell it back to the grid, and a certain amount of solar does go back into the grid, but almost all of the solar in the system at the moment is decentralized, doesn't get transmitted via the grid, and there's only about 40 gigawatt hours in total of generation that ever finds its way to the grid in a year. In future, the removal of subsidies has actually greatly reduced the growth in solar over the last few years, but it is expected to grow again with a significant contribution by 2050. And some of the areas in which we believe it will help is that solar will be co-located to storage facilities, and solar power can be used to charge storage, and it could also be used for hydrogen electrolysis as well. So it's quite possible, in fact it's very likely, that solar will grow in significance in the coming years, particularly leading up to 2050. Does the plan work? That's the next question. Will all that work? According to the National Grid, all of the scenarios can meet peak demand in leading the way. But we need to look not only at the peak, but how long peak demand might be a challenge when relying primarily on uncontrollable sources, for example, wind, or finite sources such as storage. So I've taken a week in early 2020, the one we looked at just now, and I've scaled it up to 2050 using the leading the way scenario. So what does that mean? Well, total demand, excluding electrolysis for hydrogen, will have increased by 40%. Nuclear capacity will have been reduced by just over 40%. Biomass will just about have been eliminated, replaced by BECCS, so CCS biomass, with about 3 times the capacity of current biomass by then. Coal and gas will have been eliminated. Generation by wind will have scaled up by a factor of just under 6. And other renewals will be about the same. So I'll just take them as a sort of a little bit at the top that you can assume will be there. Now, what I've done there is to put nuclear, CCS, biomass and wind and the main sources of supply there. And I hope you can make out the black line. So that's the supply line, which is very often well above the red demand line. So that's where your excess offshore wind comes from. That's where you can electrolyze your hydrogen. The problem is that we still have some reds above blacks. We've got one there, we've got another one there, we've got another one there, and so on. So how are we going to deal with the reds above blacks? Well, we call on interconnectors. The largest deficit in that case was 32 gigawatts. And in the leading the way scenario, the maximum capacity available from interconnectors in 2050 would be about 27.2 gigawatts. If we could get all of that, we could just about plug the gap just using interconnectors. And if we use all of it, note that little pale coloured line at the bottom there, that's the use of interconnectors. See those 3 peaks there? Suddenly we're using almost 30 gigawatts of interconnector power, and that just nudges our supply up to the demand line. It's just slightly under in places, but a little bit of storage, a little bit of others will cover that. So that pretty much works. However, it makes that big assumption that we can get all of that interconnector power, which I personally have a certain amount of doubt about for reasons that I will come back to a little bit later on. If we take a week 2 weeks later, so this is the equivalent of week commencing the 20th of January 2020. Let's do the same exercise, but look at it this time. Look at the black. Wind was poor in that week. It wasn't the poorest it's been. It was a sort of below average week for wind. But although it did all right at the weekend, during the week, Tuesday, Wednesday, Thursday, you can see wind's a disaster. It's this green line here where it's bumping along below 10 gigawatts in some places. But look at the gap we've got now. It almost never covers our demand, the red line. So let's kick in the interconnectors again. Let's once again assume we can use all of that, which is, say, rather unrealistic. Let's see where we get to now. Now we can see the scale of the problem. We've got 3 big peaks that we can't meet, those 3 big red peaks there, and we're way below them, all 3 of them. So how are we going to deal with that? even with the assumption of maximum interconnector import capacity for prolonged periods of time, demand is not met. We have 3 periods of 14 to 15 hours each when we would need to use storage, and there will be little opportunity to recharge storage between them. So we'd be using the storage for 14 or 15 hours. Most of it would have run out by then anyway, but we wouldn't have a chance to recharge it again. And bear in mind, this isn't the worst week we've had by any means. The use of all available storage, even if it was fully charged at the start of the week, would still not be enough to keep the lights on. This is a more difficult week than the one we looked at before, but there have been many even worse ones. In 2050, the leading the way scenario forecasts a total storage capacity of just over 200 gigawatt hours, excluding vehicle to grid. Although how much power we can get at any one time depends on the type of storage. That table at the bottom is important. At the top, you have battery storage. So this is using what are basically conventional batteries. Come back to those in a little while. The planned storage capacity is 56.2 gigawatt hours. And the capacity to actually generate is 25.3 gigawatts. So generating the maximum amount of capacity, battery storage can last a couple of hours, just over 2 hours. Now, we wouldn't need that amount for all of those periods. We'd need about half of it, but that still only means that battery storage would last 3 or 4 hours. Liquid air, compressed air, and pumped hydro can only generate capacity at round about the 4, 5, 6 gigawatts level. So they could work for a certain amount of time. Liquid air could do 3 or 4 hours of its capacity, compressed air about 6 of each. But as you can see, none of those is really going to plug those gaps. The only one that can make a really significant contribution is vehicle to grid. And even that, working at its maximum, can only do probably one of those periods. If every vehicle to grid facility in the country were used to the point that every car, every battery electric vehicle in the country used all of its power that was made available for vehicle to grid, we could deal with one of those deficits, about 15 hours, roughly 14 or 15 hours. So in that particular week, I suppose the storage might just squeeze through, but it's an extremely idealized set of conditions we need to do that. And remember, that's only if we can use all of the internet capacity, and that's only if we can use all of the internet. Let me try that again. If we can only use all of the interconnector capacity when we need it. So with full interconnector capacity and pretty much all the storage we could possibly have, we might scrape through that week. So you're probably starting to see some problems. I hope so. What particular problems do we see, and what could we do about them? Well, the fundamental problem is intermittency. It's that pattern of demand. And it can only be overcome by having sources that are controllable, ones that we can basically move up and down. And the plan puts this job into the hands of interconnectors and storage. Now, I've already talked about some of the issues with interconnectors. In 2050, the leading the way scenario shows an interconnector import capacity of just over 27 gigawatts. One of the other problems is that the forecast is for us to be exporting more interconnector energy than we're importing. The assumption is that we'll be exporting more than we import. So it's extremely unlikely that we'll always just be able to switch on import whenever we need it, particularly because based on current evidence, we'd need it not just every week, but almost every day, particularly in the winter. And although there are agreements on how much energy will be traded over a period of time, there is no guarantee that interconnector import capacity would be available at any particular point in time. So how likely is it that Great Britain will always get to choose which way the energy flows? And the other point to bear in mind here is that all of our interconnector partners are still using non-renewable sources to provide us with power. Now that may change by 2050, but we are importing energy which is not fossil free. Any of you that used electricity yesterday or the day before, I'm sure that's most of you, you will probably not realize that some of the electricity you used was actually generated by burning peat. That usually people are horrified of that, and they say, well, I get my electricity from Ecotricity, it's 100% fossil free. Well, it isn't. It's the same electricity the rest of us to get. And yesterday we got quite a bit from the Republic of Ireland on Monday and Tuesday. In fact, most days last week we did. And some of that electricity is generated by burning peat. So bear that in mind for one thing. But the other thing to bear in mind is that our interconnected partners are also trying to achieve the same thing we are, net zero. So they're going to be very careful about importing and exporting as well. Will we have enough storage capacity? The most significant volume of storage is to be provided by V2G, vehicle to grid. If you haven't heard of that, basically what happens is you plug your battery electric vehicle battery into a supply, and you say how much of your battery power you're prepared to return to the grid. And using a sort of very smart meter, the grid can grab some of your electricity out of your car battery. And the amounts you saw, I showed you in the table just now. Although this is technically already implemented, it's already available and proven and so on, I have certain behavioural doubts that anybody, knowing they had a quiet week coming up, would return the power from their electric vehicle to the grid. But anyway, that's just me being suspicious. So how likely is it that BEV owners will have enough energy stored in their batteries when electricity supplies are stretched to return some to the grid? I think that's quite a good question. When it comes to battery storage, I'm going to be running short of time, so I'm going to just whiz through this bit quite quickly. At the moment, we have very little battery storage available on the grid. We're forecast to have 56.2 gigawatt hours of battery storage on the grid. We are about to see the start of a new battery storage facility to be built by Intergen on the banks of the River Thames. This will be the largest battery facility in Europe when it's commissioned in 2024. It will provide just over half, it will provide 640 megawatt hours of energy, so it can store just over half a terawatt hour. And sorry, just over, let me try that again. It will provide 640 megawatt hours of energy and be able to provide 320 megawatts of power. So it will be able to provide that for 2 hours. There is a potential to expand up to 1.3 gigawatt hours, so to roughly double that capacity. So of our 56.2 gigawatt hours, that's roughly 1% of it when it's commissioned. So we need another 100 of those to provide the forecast battery storage capacity in the leading the way scenario. Now, one of the clinching things about this is that this particular battery array is going to use lithium-ion batteries, and I'll come back to that later. And another critical part of that is that Intergen is a part Chinese-owned company. Now, will Great Britain be too dependent on unproven technology too soon in the leading the way scenario in this approach? There are two major technologies at the foundation of the current plan to 2050. There's BECCS and there's hydrogen, particularly green hydrogen. Neither of these has yet achieved any level of use at the scale that will be required, and I believe they introduce a high level of risk to the plan. Potential issues with BECCS include it's still not proven at a very large scale. We would need to devote large areas of land to this to produce the biomass. Currently, in a trial project at Drax that I'll talk at the moment, they're actually getting wood pellets from the USA. Would we need to displace communities to generate that amount of biomass? Will we affect the biodiversity? Will it increase the demand for water? Will we need to use more fertilizer to grow this biomass? And will air pollution due to combustion of the biomass and biofuels involved be a problem? And there are, as usual, geologic storage concerns. For example, will this stored carbon be subject to leakage issues? So we have a trial project going on at Drax in North Yorkshire. It was started in October 2018. The first carbon captured in early 2019. There's a second Drax pilot going from biomass feedstock. It was due to be installed in the autumn of 2020. I haven't heard whether they've actually managed to capture carbon in that second project yet at any kind of scale. So maybe one of you has heard, but the aim is to have BECCS technology installed on at least one biomass generating unit at Drax in 2027, and to be in some level of at least prototype production at that stage. Bearing on what I said earlier about having all this working in prototype form this decade. There is a very helpful process diagram, if you don't know about BECCS, on the Drax website. It's a really good way of explaining what BECCS is all about. Those of you who are familiar with the use of hydrogen will know that there's a relatively small amount produced at present. It's mainly used locally as a feedstock for industrial processes. Its transportation, as I said earlier, is one of its great advantages, but at scale, it's quite a big scale thing because hydrogen is not very dense. It's often converted to ammonia to be transported. And there are still some uncertainties around the cost, efficiency and deployment challenges of the alternative production methods. There's research in progress at the moment, but there's still no agreement about the best way to be producing this hydrogen. Of course, hydrogen is highly flammable, which is a bit of a disadvantage to say the least. And it's more difficult to contain than oil, so it tends to leak out of containers. Let's look next at materials issues. I've mentioned battery electric vehicles, and I've mentioned lithium and so on. Many of the technological changes that are embedded in the plan have materials issues to resolve. Insufficient materials for batteries for electric cars. Now, there's always a lot of controversy on this subject because I raise this and people say, no, there's plenty, there's so many trillions of tons of lithium in the planet. Lithium is quite a difficult material to mine. It's mostly extracted from brine, a lot of it coming from South America, some from Australia and so on at the moment. But the reserves of it are actually relatively very limited. And if you've looked at recent press, if you look at sources like Forbes.com and others, you'll see that there is a looming shortage of lithium. Price is likely to go up. And the use in battery electric vehicles is skyrocketing. The supply isn't. And not only is that a problem, but we're also talking, if you take the Intergen project that I talked just now, about using lithium for stationary storage, battery storage as well, which isn't going to help. And other products involved in this, cobalt in particular, which, as you may know, there was a lot of controversy over the mining of cobalt in the Democratic Republic of Congo using child labor. And the DR Congo produces the majority of the cobalt that's used in the world at the moment. So this is a very controversial area, the area of materials. And road transport issues, materials for batteries, charging infrastructure for BEVs. We're talking about going non-petrol, non-diesel by 2030, but we have only quite a small proportion of the required charging infrastructure in place so far. I know a lot of it's going in, but something like 35% of car owners in Great Britain do not have their own land they could charge a car on. So they don't have a garage or a driveway. And there are issues about how they're going to be able to charge their electric vehicles. People say, well, they can charge them at work or go to the petrol station. But then you need to think back to that question of the demand peaks on electricity and so on. So could the need to charge EVs cause worse demand peaks? The other factor in this is if we're going to start switching commercial vehicles to using hydrogen, we need a distribution and supply infrastructure for that. I'm not sure if the information I'm giving you just now is completely accurate, but last time I looked, there were about 10 hydrogen, if you like, hydrogen pumps for public use in the whole of the UK. I think it may have gone up a few since then, but there are a few test areas where you can charge a hydrogen-powered vehicle, but there are very few. Let's look at road transport energy demand now. 2019 at the top. Oil and petroleum, 423 terawatt hours, tiny bit of electricity, 16 in biofuels. Look at leading the way. This is for road transport, so it includes cars, vans, heavy goods vehicles, buses and motorcycles. Look at leading the way. No oil and petroleum, 81 terawatt hours of electricity. and 45 terawatt hours of hydrogen. So we've gone from one situation to a completely and totally different one in 2050. It's a huge leap. I'm not saying a huge leap's not needed, but it's a huge leap. Nuclear power is also a concern. Nuclear power provides a significant and relatively reliable part of our baseload at present. Most existing nuclear plants are scheduled to close in the 2020s. Hinkley Point C is scheduled to come online between 2025 and 2030. Leading the way assumes that more nuclear facilities will come on stream. So we're not losing that capacity, but we don't know which ones, because all of the others are either in planning stage or there's some sort of review going on. We have nothing else certain. Hinkley Point C, there seems to be a reasonable level of confidence that it will actually materialize, but we'll need more than that to keep our nuclear power levels up. Other questionable aspects of the plan, well, I'll lead you to read the slides here. Marine sources are making a major contribution. It's hard to know where that's coming from. The larger projects like the Severn Barrage have been abandoned, and marine, to see it grow to the extent that it's supposed to, that will really be quite a surprise. So what does this do for greenhouse gas emissions? If we look at 2019 greenhouse gas emissions, the top row there, we have a total of 480 million tonnes of CO2 equivalent. If you look at leading the way, heat for buildings will contribute nothing instead of 87. Electricity before the application of BECCS will contribute 2 instead of 57. Industry contributes 4. Other contributes 45. But the whole thing is saved by the minus 61 of BECCS. So that's the amount of carbon that's captured and thrust away underground, and that gives us minus 10. And you can see what the other scenarios achieve there. Note the little point at the bottom there. Other in this case includes aviation and shipping. Aviation and shipping are going to continue to be a problem, and that's why they have the big pluses in them. So key points from the national grid. I'll let you read this slide because this slide and the next one, because they really repeat some of the things that I've said already with a few more numbers in them. But summary of the major issues: intermittency of wind and solar will continue to be the prevailing issue for me. The dependence on interconnectors, I think, is a huge dependence which needs very careful consideration. The storage is inadequate, particularly if V2G doesn't really take off. BECCS is new and unproven. Hydrogen is relatively new and unproven. Materials for batteries could well be an issue. And there are transport issues such as the charging infrastructure. These are the things that I consider to be the most important ones, plus continuity of nuclear capacity. And then the one problem that I think is the biggest problem of all, somebody needs to manage all this. Because at the moment, the government's approach tends to be, we're going to leave it to commercial interests. And I don't think that will work. I'm not saying it's not primarily a commercial issue, but somebody needs to grab hold of this and make it work. And really, that's it. Question and answer time. There's a website link to a website that I contribute articles to there, which has got a lot more information about all of these things. I'm afraid it does tend to be rather anti the National Grid's plans, but that's because I think there's plenty to be anti in them. I do respect what they're trying to do, but what they're trying to do is incredibly difficult. So that's it.
Thank you very much, Lawrence. Just a quick question from me before I look at the questions we've had on the chat box. Is the GridWatch website still up and running?
I believe it is, yes. I don't really use it very much. There are 2 or 3 sites. You mean the one that displays the live what's being burnt?
Yeah.
Stuff. There are 2 or 3 of those. I can send you the links because I do look at them. I don't watch that particular one because what I tend to do is to look at the daily figures from Elexon, which is the official source of those.
It's just that if anybody is interested, the easiest way to find it is just Google GridWatch as one word.
Agreed, yeah.
And it'll give you all sorts of graphs and things.
I believe it's still there, and there are 2 or 3 others as well, which are very, very useful, very interesting, yeah.
Right. Going to the questions then. Some of them you've answered part of the way through. Peter Beveridge raises a point. He says if the perovskite solar panel reaches 40% efficiency, this would be a game changer for solar. So I'm guessing that would up the capacity of solar panels. I have to declare an interest here. I've got solar panels on the roof.
Yeah, solar is one of the things which, if you look at load factors, which is basically the ratio of what's produced to what the rated capacity of a device is supposed to produce, solar generally operates in the region of 10 to 12%, which sounds pretty poor. And as I say, one of the things is that primarily at the moment it's used locally. I think there is great potential for solar to be used, for instance, for electrolysis, for charging storage and so on. However, I don't have any up-to-the-minute information of this, but if you look at a report, I can send you a link to it if you'd like me to, Sue, and you can pass it on to other people. One of the other issues that's been raised with materials is the shortage of materials to make solar panels. Because one of the things to bear in mind in relation to this, as with the batteries, is the scale of what we're going to be making is going through the roof. And it's not just, we need twice as much as we did 5 years ago. We need twice as much as we needed 3 months ago. But there was a very interesting article I read from Professor Harrington, I think it's Harrington or Harrington, last year about materials for solar panels. So yes, better solar capacity would definitely help if we can get the materials to make the panels.
Yeah, I have noticed quite a few fields full of solar panels appearing over the last 5 years.
Yeah.
So obviously somebody's doing it.
That's
Mark
right, yeah.
Lewis was asking about who are the lovely people who provide energy into the interconnectors. From memory, on GridWatch there was France and the Netherlands.
Yeah, I can tell you what they are. There's a Moyle one to Northern Ireland. There's one to the Republic of Ireland. There's one to the Netherlands. There's one to Belgium, and there's one to France. And just for general information, France gets most of its electricity from nuclear sources, so that's unlikely to change that much, although like everybody else, France is trying to get to net zero as well. So France is relatively clean. Belgium still burns a lot of coal, and believe it or not, the Netherlands burns a certain amount of coal as well, although both of those are very enthusiastically heading for net zero. Ireland still burns coal and peat in the Republic. I don't think Northern Ireland burn any more peat. Ireland, it's still a bit of a scandal over there. People very annoyed that they're still burning peat. I think the last figure I heard or read was that they're going to stop burning peat for electricity by 2027. The other thing to bear in mind, and I don't really have any reliable sources on this, the last time I read about wind in Europe, the limited amount of research that's been done suggests that when we have low wind in the UK, there's generally at least as low wind in Western Europe as well. So when we have wind lulls, which are going to cause the sort of issues we saw there with very low wind generation, it's not necessarily the case that our European neighbours are going to have electricity to spare. So that's one to be a little bit careful of as well. Obviously, we don't know what's going to happen, but we can only get interconnector power from other people if they've got it.
Yeah, that was a comment made as well, that only if they choose to supply it to us.
Yeah.
And the same with cars as well. If people choose to supply electricity from the cars or not. So that's really something you're not going to have control over, isn't it?
I think people are going to be very cautious of the whole V2G thing. Just one other point on the previous subject. There was an article on the site that linked you there about coal, and just putting in perspective the idea that we've nearly stopped using coal. If you look at the National Grid site, they talk about exporting interconnector energy to use our excess energy. Well, all the time that we were exporting electricity using the interconnectors last year, for the whole time, we were burning fossil fuels. We were burning fossil fuels all the time anyway, but for 40% of that time we were burning coal. So if you were being really cynical, you'd say that for 40% of the time we were exporting electricity last year, we were burning coal to do it. So to me, that's just, well,
Crackers,
it's
yes.
crackers. Exactly. Couldn't have put it better. I was going to use a stronger word, but crackers is a good word. Yeah. Yeah. Okay.
Stuart Millman is asking, what is the historical level of overcapacity in the grid?
I could find out for you. I don't know. I mean, the overcapacity at the moment, obviously with things like wind, unfortunately, it tends to get thrown away. So, or not used, I should say, or a certain amount of it does. It would be very useful if we could find some way of using that. I don't know. I don't have figures on overcapacity, but I'll see if I can find them and I'll forward them on.
Right. Stuart's also asking, is anyone investigating CO2 methane to give chemically useful carbon monoxide as an alternative to BECCS?
I don't know, but I can certainly find out. I have a source that I can find out on that. I know that primarily, actually, if you look at the National Grid's main document, it's like a 40 megabyte PDF file. It's a huge document. There is a section on that which talks about alternative ways or alternative options for BECCS and alternative options for hydrogen production as well. And that's very interesting because with leading the way, the idea is to try and do things in the most low carbon way possible. I don't know much about CO2. In fact, I don't know anything about CO2 methane. So I'll have a look at that and see what I can find out.
Right. Peter Chandler is asking, if carbon capture cannot be resolved successfully, we are in for a major shortfall, question mark?
Absolutely, yeah. Absolutely. I mean, we're riding on two. I think to some extent hydrogen is less of a risk in the sense that we do know something about it. But I mean, BECCS is just a great unknown. Just to put this in perspective again, I've been following the Future Energy Scenarios documents for quite a long time, for a few years now. And when the 2019 one came out, so that's not the most recent one, the one before, the pattern in that was totally different to the 2021. I got the 2021 and I opened it and I thought, what the heck is BECCS? Where did that come? Well, I knew what it was, but I thought suddenly this thing has appeared, which is more or less half the solution and hydrogen's the other half. And suddenly, from almost nowhere, they are the two things that are going to save the day. And I'm looking at it thinking, well, let's hope they will. But there's an awful lot, we've jumped out of this plane without parachute, something on our backs, which we're told is a parachute. But I think it's a heck of a risk because there is virtually no proving of BECCS at any scale at all. And there's not really proving with hydrogen. I mean, things like electrolysis out at sea, storing it on floating hydrogen tanks on top of the sea. I mean, it sounds like Star Wars, really. And yet now that's what we're relying on working.
Yeah, Mark Lewis, I think, is in agreement with you. He says, I have a problem over biomass availability. This seems absurd.
Yep. Well, one of the things about the Drax project, which is another controversial thing, is that we're currently using these wood pellets from the States. And although I obviously haven't been and had a look myself, there's varying views of what sort of wood these pellets are coming from. And although the argument is, well, they're pellets and the wood that they're from is being replanted, people are talking about the huge timescale cycles of all this happening. And of course, the huge volume of biomass that's needed. I mean, we're talking about tons and tons and tons of wood pellets to run a prototype project. I mean, the volume of biomass that's going to be needed is huge, hence the issues that were raised there about how much land will it need and what will it do to drainage, water supplies, how much fertilizer will be used. There's a great lack of detail in a lot of these things. I mean, the numbers are there, and to some extent, if you don't ask too many questions, the numbers seem to add up. But the actual practicalities of how you're going to do it, that's something else altogether. And there are many other practicalities as well. For instance, if you look at the National Grid's figures on wind generation, they make all sorts of assumptions about wind, like that the the turbines don't deteriorate, their performance doesn't degrade. Well, the evidence is that it does. It doesn't degrade a lot, but in 25 years of life of a wind turbine, it degrades probably something of the order of a half. Now, none of that is accounted for, you know. So you look at it and you think, we're doing something that probably does it on a knife edge. It's a lot closer than I'd like. It'd be lovely to draw those diagrams and say, see how far the black is always above the red. It's always way above. You know, it doesn't even matter if that's not quite right. We'll still be fine. That's not the case at all.
No. Paula asks, if you were to change one thing, what would it be?
Right. I'm going to cheat on that. And it's a terrible cheat, I'm afraid, because I don't have a solution to this that anybody would actually like. I can't say to you this is what should happen. My objective in all of this is to get people, as many people as possible, to say this won't work. We're going down a road which is pretty much the only opportunity we're going to get, and we need to do something that's got a good chance of working. Now let's take the case of cars. Cars are a very good example of this. People talked about hydrogen cars instead of battery electric vehicles. And if you talk to people about hydrogen cars, they say they're going to blow up. There's this flammability issue with hydrogen, all sorts of problems. And, you know, I don't know enough about it to have a strong opinion one way or the other. Some people love them, some people loathe them. I think we can be pretty certain that battery electric vehicles won't work at this scale. And therefore, I would say, if we know it won't work, what's the point in producing billions of lithium-ion batteries we've got to throw away in order to get along a road that's a dead end? Now, a lot of people will disagree with me. I have the most arguments I have are about materials for car batteries, because some people say we'll find a way. Maybe that's the case, but we're talking about lithium, and I think the evidence is that there just isn't enough of the stuff available at the rate we'd need it. If you talk about hydrogen cars, at least the use of hydrogen seems to me that it might have a future. I don't know enough from an engineering point of view to say whether the risks are too great or there's going to be this problem or that problem, but at least you can't rule it out on the basis of what we know now. You could at least look at ways of overcoming the problems. So I would say, let's not go down any roads that we know won't work. I don't know that BECCS won't work, but I'm very suspicious of it, particularly from the point of view that you just mentioned about the amount of land use involved and so on. I'd be much more likely to say the one thing we need to do is to be able to avoid the things that are going to wreck the planet. You know, the things that are really going to cause the most damage for the least benefit. There are many things that we can do, day-to-day things, even looking at conversion of heating in homes and so on. There are many things we can do that are just a change. We just need to get used to doing things a different way. There are other things which not only are going to cause a lot of damage, but they'll be pretty much irreversible in some cases, and they're not going to work anyway. And so I'm cheating on the answer. I'm going to say the one thing I would do is to work out what's impossible within a reasonable scale and say, we can't possibly do that. We need to do something else. But don't ask me what the something else is, please.
Right. Peter Chandler comments, the gas industry is steadily increasing hydrogen content of mains gas. Could the Middlesbrough Hydrogen Village change the future for us?
I don't know about that. The one thing I did read recently, which was very interesting, is that there are thoughts that the existing gas infrastructure, the pipes and so on, could actually be used to carry hydrogen. I don't know whether any engineers there can confirm that, but that would be a very big plus if we could actually pump the hydrogen along existing pipes. I've no idea whether that's true or not. I think the answer to the increased proportion of hydrogen and gases, I'm not technically aware enough to know, but I'd be interested in whether some of the gas infrastructure would be usable by hydrogen.
Yes, I think it would. We had a lecture about that a while ago, and there was a feasibility study being done on how they would convert Leeds from town gas, well, from natural gas to hydrogen, and it was a similar sort of project to those of us who remember being converted from town gas to natural gas.
Unfortunately, I
So,
do.
people would need new jets and things in the boilers and gas cookers. But yes, I think it is possibly doable. Himank Kulkum has just checked that we're getting 5% of our energy from France right now. So that answers the question about where from.
That surprised me, yeah. If you look at the interconnector use, we're getting stuff from interconnectors most of the time now.
Yeah.
Having said that, we're exporting quite a bit as well.
Yeah. Will heavy industry continue to pay for the extended rollout of offshore wind turbines? Asked Stuart Milne.
Yeah, that's an interesting one, because as you see, if you go with this hydrogen electrolysis argument, you could argue that there is a continuing good case for more offshore wind, because rather than, I mean, I think we need to get past the point of thinking that offshore wind, or indeed any wind, can plug all these gaps, because it can't. We know if it's not windy, we don't get energy, that's it. But if we could use more of what we don't need, we might be able to help it level things out. In terms of paying for it, I read a paper literally this afternoon, just before here, that somebody sent me, which basically talked about the misleading accounting of the cost of wind in general, offshore wind in particular, and the fact that offshore wind is actually costing us a lot more than we think it is. And I think that the answer to that is that, first of all, we do need a much more straightforward and believable accounting for what offshore wind is costing us. And then I think if we could look at the extent to which offshore wind, in particular in the future, could do things like electrolyze for hydrogen and so on, maybe offshore wind would be a better bargain than we think it is, because it would actually be doing two things then. But that's obviously quite a complicated calculation I couldn't begin to do now. But it's a very interesting question. I mean, wind is costing us a lot of money, and it does some good, but it can't solve the problem on its own.
Right. A question from David Alford. Why do we not use more hydropower, tidal and rain? I've never heard of rain being used. I must admit I've wondered why we don't use tidal, and also why we don't use more river water for generating electricity. I went along the Danube and the Rhine a few years ago, and they have weirs and hydroelectric everywhere, and you're using the same water again and again and again.
Yeah.
I guess our rivers aren't as big as that, but we just don't seem to do that sort of thing very much at all.
No. I'm just, can we still see the slides? Do you know, Sue?
Well, yes, I can.
I've just gone back to an earlier slide. Amongst the more surprising elements in the plan for 2050 is the presence of marine sources. At the moment, we have only 25 megawatts of marine. By marine, I mean tidal and wave power. And there's only 25 megawatts, which is a tiny little speck in production. And it's forecast to be up to about 10 gigawatts in 2050. Now, I don't know where any of that's coming from, because the substantial projects, such as the Severn Barrage, the Severn Barrage, last I heard, it's actually been abandoned. And some of the other bigger ones are either back in planning or trying to get funding or whatever. The bigger wave and tidal projects seem to come against the most environmental opposition, and very often they seem to be defeated. The smaller ones, there are some pilot projects, particularly up around the coast of Scotland and so on, but they're all fairly small. A lot of lagoon projects and so on, generally very small. But even if all of those work, I don't see how they're going to add up to 10 gigawatts by 2050, but 10 gigawatts is still a relatively small proportion. Wave and tidal, particularly wave, have tended to be seen as very expensive projects in terms of both infrastructure, putting whatever it is on the bottom of the ocean or floating on the top of the ocean or whatever, and then maintaining them. In terms of hydro, my understanding is that we just don't have enough rivers with enough drop to make it worthwhile. I once did some voluntary work out in the Far East, and we had a river that flowed past our camp, which had a drop of about 10 meters. And I think we used it to run a light in the evenings or something like that. And somebody explained to us how much hydro drop you need to do to power anything. The hydro situation, as I understand it in Great Britain, is that the cost of setting it up and the amount you could actually do on any rivers, given that we don't have that many rivers with that much of a drop, would not make it economically viable. And what there is already in place. I'm working from memory now, but I think the figures are something like, by 2050, I think it's something like 1.5 gigawatts of hydro is forecast. So it's a useful amount, but it's still not a lot. I think it's 1.5 gigawatts, something like that. And the other version of hydro is pumped hydro. Again, you'd think, why can't we use our excess energy to pump water up to the top of the hill and then it run down again? The problem with that is we don't have enough mountains that are big enough to make it worthwhile, apparently. So
there's one in Wales.
Yeah.
Trosfinid.
Yeah, there is. If you look at the GridWatch, there is a certain amount of pumped hydro at the moment, but it's quite a small amount, relatively speaking, a small amount. And of course, I think the last I read was that what pumped hydro it's worth doing is in place already. I could check the actual growth figures. I'll find you what the pumped hydro growth figures are, because that may have some capacity. But last I read, it wasn't very much.
Right. Mark Lewis comments, hydrogen cars do not explode. Petrol ones are much worse.
Well, there we are. Exactly, yeah.
There we are.
Yeah.
Peter Beveridge comments, what we're trying to do is bigger than any other human endeavour, and we'll have to put everything on the table.
Yeah.
Very true.
Yeah, absolutely. I think the other thing about this is all the evidence is, I mean, some people deny we're having global warming. Some people say, well, what difference does it make in the UK because we're a tiny part of the problem, all those things. From my point of view, we need to do what we can, but we may well only have one go at it now. We may, we can't try this, and if it doesn't work in 10 years' time, say perhaps we should have done hydrogen after all, or perhaps we should have done it all with wave and tidal. We won't get another chance. And that's why I think we need to get it right. What we do needs to be right. And it needs to be enough, but it needs to be right.
Yep. Mark Allen asks, have you done any modelling on demand side management, including load shedding? Wind is uncontrollable, yes, but, well, he says quite predictable. It depends how good a weather forecast you've got, I suppose.
Yeah, it's proved notorious. I'm just going to go slightly off track for just a moment, and possibly be unfair to one or two people at the National Grid. The National Grid have a modelling team, and they model things where they say that this is going to work or that isn't going to work. We do modelling ourselves. Obviously, we've got a smaller team than the National Grid have. But one of the things that we do is to use past year's actual weather. So we record what the wind was, what the sunlight was, and so on. We get that information from reliable government sources. And we say, as I've done in this presentation, if what happened in 2020 happened in 2050, would it work? Now, I don't think the National Grid do that. I apologise to the National Grid if they do. I think they tend to take more, not quite idealised situations, but sort of average scenarios, because if they did what we did, they would realise that even for recent years, like 2018, 2019, 2020 now, this doesn't add up. It doesn't really work. I mean, you've seen what it's like using the figures that I've used, and assuming that I've done them correctly, you can see it's not quite right. It just doesn't work. In terms of the demand side modelling and so on, if you look at the National Grid documents, they actually do things like, with a case of BEVs, battery electric vehicles, they model different charging patterns. So if everybody charged at 2 o'clock in the afternoon, and some people did it overnight, etc., etc. So they do an element of that. We do that in a very, very limited way, and it's one of the things that we're going to do more of. It's very time consuming, of course, but at the moment, what we're really saying is that whatever you do, it won't work. If we got to the point that we could say, well, if you could change the demand profile, say drop the peak by 10%, correspondingly push the bottom up by 10%, would it work? Then that would be great. And that's one of the things we want to be able to do. We haven't done it so far. But I think that part of the solution to me must be leveling that demand out somehow. There has to be a way to stop those peaks. In terms of predicting the wind, well, I live in North Yorkshire. You're probably most of you live in the northeast as well. I trust the wind forecast for what's happening outside now, and I've probably got an idea of what it'll be like tomorrow. But even if you could forecast what the wind was going to be like tomorrow or the next day, you probably couldn't change it. And what it does is possibly at least as much problem as knowing what it's about to do. I think the idea of having very responsive supply sources, so being able to very quickly, as pretty much happens at the moment, I mean, the switching, the stabilization of supply and so on is absolutely amazing. I know there was a bit of a disaster once last year, but there's a heck of a lot of automated, very clever switching going on at the moment, and the more of that, the better. I mean, that's absolutely great and essential, of course. But it doesn't mean the fact you can quickly switch to a battery or to an interconnector doesn't mean there's enough power there to keep you going long enough.
One last question then from Ruben. About 15 litres of water are required to produce 1 kilogram of hydrogen from electrolysis.
Yeah.
Have the government strategies looked at the impact of hydrogen on water infrastructure and water scarcity in the future?
I have no idea, but that's I should have thought of that myself, because as I said right at the beginning, I'm one of the people who does the sums. Do you know, I've never looked at working that out, but that's very interesting, isn't it? I will, because we've got the figures for how much hydrogen we're aiming to produce. I'll try and find out, and I will get back to you if I can find an answer to it and perhaps put my own sort of numerical spin on it, but I don't know.
Right. Okay. Well, I think at that we seem to have more or less run out of questions. Oh, Mark Allen comments, when you burn hydrogen, you do get hot water back out, though. So whether you can recycle it, I don't know. Anyway,
As far as I'm concerned, we'll make tea with it.
That sounds like a good idea to me. And on the subject of tea, I can smell mine downstairs.
Yeah.
I think at that point we'll say thank you very much, Lawrence. That was a most interesting talk. Raised lots of issues that I'm sure people have never thought of, and what worries me is that government have probably never thought of them either.
No. It's very worrying when you think about things like this, thinking today about the school meals and how much thinking has gone into that, and you think, if they can't even figure something like that out, how can they possibly do this? But anyway, perhaps we just need to nudge them a bit more.
Well, yes, I think so. Anyway, thank you very much indeed, Lawrence. That was great.
Okay.
If anybody wants any information that Lawrence is going to pass on to me, please do email me, sue.parker2911@gmail.com. It is amongst the chat stuff if you scroll up and down and look at it. Most people seem to have found the chat, I think, judging by the comments that have been coming and going. So at that point, I'll say thank you very much, Lawrence, and good night, everybody, and belated Happy New Year. Take care and stay safe.